Hello, we're going to introduce the divergence of a harmonic series with only primes, and my name is Cai Dong. It's more well known that the harmonic series diverges, but it turns out if you limit the sum to only primes, and it also diverges. We're going to do that using three inequalities which we will provide in this video. The first one says that the sum k equals to 1 to n of 1 over k. In other words, the n partial sum of the harmonic series is less than or equal to this product over all primes, which are less than or equal to n of 1 plus 1 over p, and then the sum as m goes from 1 to n of 1 over m squared. Let's get to proving this first inequality. I'll start by noticing that if k is between 1 and n, then we can write k as either a perfect square or a perfect square times product of distinct primes. So what that means is we have k equals to m squared. That would be the first case, and that's where m is less than or equal to the square root of n. Then k is equal to p1 times m squared, where p1 is some prime which is less than or equal to n. Or k could be equal to p1 times p2 times m squared, where p1 and p2 are both distinct primes less than or equal to n, or so on and so forth. So k could be a product of our different primes that are all less than n as well. Now we're gonna take every term of our harmonic series, 1 over k, and rewrite it depending on if it's a perfect square. A single prime times a perfect square, the product of two distinct primes times a perfect square, or so on and so forth. Now we're going to change equality to inequality, so we don't have to worry about the bounds. We have the sum k equals to 1 to n of 1 over k, so that's going to be less than or equal to this sum, as m goes from 1 over 1 to n of 1 over m squared, and that would be the case where k is a perfect square, plus the sum m equals to 1 to n of 1 over p 1 times m squared, where p1 is a prime less than or equal to n. So that would be the case when k is a single prime times a perfect square. And then you can see this is going to be the sum n equals 1 to n of p1 p2 less than or equal to n, and then 1 over p1 p2 m squared, where p1 and p2 are distinct primes, and then plus so on and so forth. Now that we've done this, and since we have a finite number of these sums, given that there are only finite many primes that are less than or equal to n, this right-hand side of the inequality will factor as follows. Now, I can just go ahead and write that this is equal to the product, as p is less than or equal to n of 1 plus 1 over p times this sum m equal to 1 to n of 1 over m squared. So let's notice if we were to expand this out, it looks a little bit like this. We have 1 plus 1 over p1, where that's maybe the first prime less than or equal to n times 1 plus 1 over p2, all the way up to 1 plus 1 over pr, where p1 to pr are complete list of primes that are less than or equal to n. And then notice that's being multiplied to 1 over m squared, where we've distributed that through every term of the sum. Now notice by choosing the correct number of ones and the correct primes, we can retrieve all the values of k there. For example, if we need k to be just p1 times m squared, then we'll take this 1 over m squared multiplied by all of these ones. But in the last case, we multiply 1 over p1. So hopefully that gives you some kind of feel of this product of the 1 plus 1 over primes.
Hello, Professor. My name is Huang Qiyou. My student ID is 111061201, and I'm going to introduce the second inequality and the third inequality. So let's start with second inequality. We have the sum m equals 1 to n of 1 over m squared. So the first thing I'll do is to take the first term out of this sum. So we have 1 plus the sum equals 2 to n of 1 over m squared. Then I'll replace the denominator of this fraction with something smaller, thus making the fraction larger. So we have 1 plus the sum m equals 2 to n of 1 over m squared minus a quarter. And it is larger than 1 plus the sum of m equals 2 to n of 1 over m squared. Now I'm going to multiply both parts of this fraction by 4. So here we have 1 plus the sum m equals 2 to n of 4 over 4m squared minus 1 here. Then we can do a partial fraction decomposition. So we get this is equals to 1 plus the sum m equals 2 to n of 2 over 2m minus 1 minus 2 over 2m plus 1. The following is this. Now we can bring this and the n down. So we have sum m equals 1 to n of 1 over m squared is less than 1 plus the sum equals 2 to n of 2 over 2m minus 1 minus 2 over 2m plus 1. So it's the second line here. And the next thing I'll do is to write our to write out the terms of the series. So we have 2 over 3 minus here 2 over 3 minus 2 over 5 plus 2 over 5 minus 2 over 7 plus all the way up to 2 over 2m minus 1 minus 2 over 2m plus 1. Okay, and then the 2/5 will cancel with this 2/5, and the 2/7 will be cancelled with the following. So we can get this equals to 2 over 3 minus 2 over 2m plus 1. So we can see here this equals to 1 plus 2/3 minus 2 over 2m plus 1. And we can just disregard this. So we have this is less than 5 over third. And now look at the left hand side and the right hand side. We have established our second inequality. Next, we can move on to the third inequality. So we have natural log of n plus 1. So now I'm going to rewrite it and make it look like an integral being evaluated. So we have the natural log of n plus 1 evaluated from 1 to n plus 1. And we can use the fundamental theorem of calculus to rewrite this as the integral from 1 to n plus 1 of 1 over x dx. So here. Then we can break it into pieces. So we have the sum from k equals 1 to n of the integral from k to k plus 1 of 1 over x dx. Here, this. Now, because 1 over x is a decreasing function for positive values, so we can just replace this 1 over x with 1 over k if we picked up an equality, because 1 over k is the largest value of 1 over x on the interval k to k plus 1. So we have the sum k equals 1 to n of the integral from k to k plus 1 of 1 over k dx here. But this is just a integral of a constant, so we get the length of the interval times the constant. But the length of the interval here we can see is 1. So we have the sum k equals 1 to n of 1 over k. Now looking at the left hand side and the right hand side, we've established our third inequality.
Now we can move on to our main goal, which is showing that the sum of reciprocal of prime diverge. My name is Lin Yisan, and we can do that by noticing that the sum of all primes of 1 over p is the same as the limit as n goes to infinity of sum over primes that are less or equal to n of 1 over p. And now we can start using these inequalities. So I want to start with the latest inequality, but instead of writing the natural log of n plus 1, I'm going to write the natural log of n plus 1. So I have natural log of n plus 1. So that is going to be less than the natural log of this n partial sum of the harmonic series. And here we can use the fact that the natural log is an increasing function. So now I will use the first inequality. So notice that it is less or equal to the natural log of this product over all primes less than or equal to n of 1 plus over p equal to n of 1 plus 1 over p, and then we have this sum as m goes from 1 to 1 of 1 over m squared, but we show that this was less than 5 over 3, so I can just go ahead and bring that 5 over 3 out there. Now the next thing I want to do is to use the fact that e to the x is bigger than x plus 1 if x is bigger than 0. To say that this term right here is less than e to the 1 over p. Okay, and then from there, what I can do is say that the whole thing is less than the natural log of 5 over 3 plus the natural log of the product over all of these prime less or equal to n of e to the 1 over p, where again, I use this inequality involving the exponential function to write this 1 plus 1 over p as e to the 1 over p, keeping in mind that I have to introduce an inequality. Now the next thing I want to do is to use the fact that the natural log will turn this product into a sum, so that is going to give me the natural log of 5 over 3, and then plus we have the sum of all primes less than or equal to the natural log of e to the 1 over p. But the natural log of e to the 1 over p and will cancel each other out, so we have just 1 over p. Now let's look at the extremely right and left hand side of the inequality we have built, and now we can use this to finish off the problem. So notice that I can move this natural log of 5 over 3 across, and that is going to tell me that the limit as n goes to infinity, or the sum over primes less than or equal to 1 over p is bigger than the limit as n goes to infinity of minus the natural log of 5 over 3 plus the natural log of n plus 1. But now we know that as the argument of natural log tend to infinity, the natural logs tend to into infinity. So what that tells us is that this turn right there is zooming off to infinity, which tells us the entire limit is infinity, which tells us that this goal series diverge and that is a good place to stop.